Hi everyone, this is lesson 6.4 from Algebra 2A, and really the topic of this lesson is continuous growth. That's the main focus here in this lesson. However, continuous growth incorporates a numerical value that we're going to learn about today, and that numerical value is given the name e. So yes, I realize e is not technically a number, but later in the lesson you're going to learn what e is and how it's used in continuous growth. So there really is a numerical value called e. Also in this lesson, we're going to be revisiting some topics from last year having to do with compound interest and annual yield. And those are thrown in there in the notes like they're really tiny, quick reminders, but they're actually pretty important parts of this lesson. So I want to take a few minutes and make sure we remember how this works. So compound interest is talking about taking money and investing it in a bank where they're going to pay you a percentage of interest. Okay? And so just to remind you what all these letters stand for, P stands for principal, which is really like your initial investment. That's the amount that you're investing. Okay. The R stands for the interest rate, and that's always given to you as a percentage. You have to make sure you move the decimal point over to make it into a decimal. And then the N, which shows up twice, represents the number of times that your interest is being compounded per year. Okay? So we're going to be talking about things like, oh, the interest is compounded semi-annually. That means you get half your interest money halfway through the year and then the other half at the end of the year. But the reason that's important is that money that goes in after the first half of the year is already in your account when it's calculated at the end of the year. So you're earning interest on top of interest. That's what compounding means. Okay, and then the last one here is T, that represents your time. And because we're measuring this as number of times per year, your time always has to be input in years. Okay, so there's our compound interest formula. And then annual yield, here's what annual yield is all about. So we were just talking about what it means to have compound interest, where you're earning interest on top of interest. That means that if I tell you that you're going to earn 5% interest, let's say, you're going to earn, so let's say it's 5% interest semi-annually. You're going to earn 2.5% interest halfway through the year, and then the other 2.5% will be at the end of the year. But when you calculate it the second time around, you already have extra money in your account from that first 2.5% that you got at the halfway point. So the total amount of interest you're earning is actually going to be a little bit larger than 5%. You're actually going to earn a little bit more because you're kind of double dipping. You're earning money on top of the interest that you already earned. So let me just give you an example. Let's say that I'm investing $100 at, I'll stick with those numbers. We'll go 5% interest, compounded semi-annually, which semi means like half. So that you're getting it halfway through the year and then at the end of the year. So that would be twice a year. Okay, so semi-annually is twice a year. So if I plug all of this information in here, so let's just point out that 5% of 100 would be $5, okay? So if I was earning 5% interest, just a flat 5% interest, at the end of the year I would have $105. But let's talk about what this semi-annual thing is going to do. We're investing $100, 1 plus, my interest rate is 5%, so for R I'm going to put in 0.05. Semi-annually means I'm compounding twice a year, so I'm putting a 2 in for N. And then I'm going to the power of 2 times, and we're just looking at this after 1 year, so I'm just going to go 2 times 1. Okay? So in my calculator, I'm going to type that in exactly how it's written. 100, parentheses, 1 plus 0.05 divided by 2, and then to the power of 2 times 1. Enter. And I actually end up with 105.05 5.0625. Okay, now technically that's money, so we would normally round it differently, but trying to make a point here. So again, the 5% of 100 would get me that extra $5. This is bonus money, okay? This is money that comes from the fact that I earned half of my 5% halfway through the year and then got to earn interest on that the second time around, okay? So I would look at this and I would say, all right, this represents the extra money that I earned. So this is an annual yield of 5.0625%. By the way, I'm only allowed to just steal that number because I started with $100. So really the fact that this number is because I would do this divided by the original 100 to get my annual yield. So annual yield is always going to be just slightly larger than your interest rate, okay, if you're compounding more than once a year, okay? The easiest way to do annual yield, so I guess let's revisit our original formula. The annual yield really can be found by doing just this kind of inner part. I guess let's write it down. The piece of the formula without the principal and without the time, basically, is what annual yield is going to be. So annual yield is always going to be this calculation, 1 plus r over n, and then just to the power of n. Because if you're just looking for a percentage, we don't need to know what we're starting with. We can think of it almost as starting at like 100%, which would be like a 1 sitting out here. And then if it's annual yield, we only want to be looking at 1 year. So essentially our time is 1 as well. When I do this calculation, I'm going to get something like 1 point blah, 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 okay? That 1 comes from here, and so the blah, 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 blah is what my annual yield actually is. So this, whatever comes after that decimal point, this represents my annual yield, okay? I know that sounds confusing right now, and when we go through and do some examples, we'll talk about that. But let's start looking at what it means to have continuous growth. So think about that annual yield concept, and you'll notice that all of these are set up almost like annual yield, except the number of times you're compounding, the n value is getting larger. So this is 5% interest compounding 6 times a year. This is 5% interest compounding 100 times a year. This is 5% interest compounding 365 times a year. Now, I'm going to do these in the calculator, but I'm not going to take the time to write them all down, all right, for the sake of this video, because the numbers themselves are not important. What's happening to the numbers is. So starting with this first one, let's slide this up. I have 1 plus 0.05 divided by 6, and then to the power of 6. Okay, and I get this 1.0510, blah, blah, blah. Okay, next one. Same thing, except now we're going to compound 100 times a year, and then to the power of 100. Okay, and then let's do the same thing with a 365. Okay, so what I want you to notice is that, so up here we did it twice a year, and we got 5.0625. Excuse me. Here we got, this would essentially be 5.105 blah, blah, blah percent. This would be 5.125 blah, blah, blah percent. 5.126 blah, blah, blah percent. Okay? What I want you to notice is that it's slowing down, that the numbers are changing less and less. Like these two are awfully close together, even though I went from 100 to 365. I could go bigger than this. I could go 1,000. I could compound 1,000 times a year. That's not realistic for a bank, but and look at my number. It's still awfully, awfully close to that. It's like the bigger this number is getting, the less this is changing, okay? And so what that means is if I'm compounding more often, it's like I'm compounding continuously. It's like I'm just compounding all the time. And that's what continuous growth is all about. And we find that this happens, that when you start making that number bigger and bigger and bigger, the value kind of plateaus, it kind of stabilizes, it stays the same. And somebody smarter than me discovered that this is based on an irrational number called E. Okay, now we're going to write down some things about E down here. But if we look at E to the power of 0.05, and we'll talk about what number value E actually is. By the way, this can be done on your calculator. Up above the ln key, you should have a thing here that says E to the power of x. So that's what I'm using. And I'm going to go E to the power of 0.05, because that was that interest rate we were using, right? 0.05. And look at my number. Oh, and I cleared my other numbers, didn't I? Let me just grab that last one with the 1,000. Look at how close that is, okay? So what we find is that these values are going to approach a particular value. They're going to get closer and closer and closer to a particular value. And that value that they're approaching can be found by doing this irrational number to the power of the interest rate. Okay, so when you're starting to compound more and more and more frequently, this can be used to demonstrate almost as if you were compounding all the time. So let's back up and talk about what the heck this E thing is now that I made you use it. So derived from the limit of this expression as n approaches infinity. That's some terminology from calculus. So the limit means as we make n bigger and bigger and bigger, as we start to make n closer and closer to infinity, what value are you approaching? So if we take this expression, and notice this time they have a 1 in there, we used a 0.05, but that's going to approach a particular value. And that particular value is an irrational number, okay? It was discovered by Leonard Euler, and this is the number that it represents, 2.71828. This is irrational. It's a decimal that goes on and on forever. It's kind of like pi. It's a famous mathematical number. It's not as famous as pi. It's like its lesser known cousin or something. But this value E, this number, when you raise it to the power of this interest rate, it gives you an approximation of what that would look like if you were compounding continuously. Okay? So, as we make the n value larger, so notice that this expression now has this r back in it, what's going to happen is this thing really becomes equivalent to just e to the power of r. All right? It approaches that, meaning we can use that to represent it. And that process of making the n larger and larger and larger and then using this in place of this is called continuous growth. Okay, and I think, do I have that on the next page? Yes, I do. So continuous growth is exponential growth, but it's occurring all the time rather than like once every year or once every month or once every day. It's constantly growing, okay? And if we go back to that compound interest formula that we had just a minute ago, and I take this middle piece and replace it with what we just said. We just said that with this piece here, if I make the n get bigger and bigger and bigger, it really becomes like e to the power of r. If I took this piece out and replaced it with e to the power of r, I would have this formula right here. That might be a little bit hard to see on the video screen, so let me just write it bigger. It's p times e to the power of rt, okay? Where p is your initial investment or your initial amount. E is that irrational number that we were just talking about, and your calculator is going to handle that for you. R is your rate. It's the same as this R, okay? It's your rate of growth. And then T is your time in years. With this type of growth, especially when we're talking banking, the e to the power of r is what gives you your annual yield. Okay, that's what's going to tell you your annual yield amount. So I point that out because I see in the first example that's what we're being asked to do. We've got $10,000 put into bonds, we've got an interest rate, and we're compounding continuously. This word here is going to be important. Continuously means I'm using E. okay, because that means that that n value is running off into infinity. So for the annual yield, I'm just going to do e to the power of r, so that's 0.0735. Okay. E, which again is above the ln key. Let me show you that on your calculator again. Here above ln, you should have e to the power of x. So e to the power of 0.0735. And I get 1.076. Let me just write this down and then I'll talk about how we actually answer the question. I'll go one more decimal place. 27. There we go. Okay. So I rounded to, I think, 5 decimal places. Probably could have been fine with 4. But this is the piece that actually tells you the annual yield. Remember that 1 is just there to show that you're growing by that amount. So I would say this is 7.627% annual yield. That would be the answer to the question. And you'll notice that that's just a little bit larger than your actual interest rate. And again, that comes from the fact that you're earning interest on top of interest. Okay, find the value of the investment after 1 year. Notice that to find annual yield, I didn't care about what my actual investment was. This is just a percentage, right? To find my value after 1 year, this is where I'm going to use this formula, PE to the power of R times T. So I'm going to do 10,000 times E to the power of 0.0735 times 1 for 1 year. I'm going to type this whole thing in my calculator just so you can see how I would do it. Notice that really I already calculated this value up here, and so I really could just do that times, this is supposed to be 10,000, I wrote 1,000. That's going to be important. So we're going to do 10,000, whoops, sorry you can't see that, 10,000 times E to the power of 0.0735 times 1. That's how I'm typing this in here. And I'm going to find that I have $10,762. This is money, so that's how I'm rounding. And 69 cents. Okay. Find the value after 3 years just means I'm going to do this with a 3. I'm going to write it down so that you have it for reference, but this is what I'm doing. 10,000 E to the power of 0.0735 times 3. So I'm just going to take that same expression, except I'm going to swap out the 1 for a 3, and that's how much I would have after 3 years. So you'll notice that with continuous growth, your money grows awfully quickly. Also, $10,000 is a pretty big investment to start with. So I'm just going to go, because there's a bunch of 9s after that, so I think I'm just going to go 467.00. Okay. Okay, example 2. So we've got $500, 8% annual interest rate, and then this question is asking me to compound quarterly, and this question is asking me to compound continuously. That's 2 different formulas. Quarterly is where I'm going back and using the original compound interest formula. So that's going to look like this. 500 times 1 plus, my interest rate is 8%, so 0.08. Compounded quarterly means 4 times a year. And then 4 times, what's my time here? 4.5 years. Okay. 500. 1 plus 0.08 divided by 4 to the power of 4 times 4.5. By the way, if your calculator doesn't let you type up in the exponent, if it just, gives you the little caret key symbol and then you're just going to keep typing, you're going to have to put that exponent up in parentheses, okay? Oh, I thought I hit enter. Here we go. Okay, so $714. Gosh, that's pretty good growth there. And 12 cents is what you would have after 4.5 years. Okay, not bad for free money, right? That's a little over $200 in free money. Okay, now let's see what happens if we go continuously. So continuously is when I replace this middle part of the formula with e to the r power, meaning that we're compounding more and more and more often and basically treating n like infinity, like we're compounding all the time. So that's going to be 500e to the power of 0.08 times my t value, which was 4.5. I would guess that it's going to be larger than this, maybe not significantly larger, but larger nonetheless, because compounding continuously earns you more free money than compounding quarterly. So 500e to the power of 0.08 times 4.5, and I end up with 716.66. Okay, so now let's circle back around to the idea of logarithms. Because we're going to eventually be working with exponential functions that have an e in them, right? So that e to the power of r thing, that's an exponential function. We're also going to want to be able to use a logarithm that has a base of e. So a natural logarithm is a logarithm in base e, and you've probably got a spot in your notes to write that down, but you're going to want to write that. And I want to point out that this is the ln key. I mentioned this key earlier and I didn't tell you what it was, but ln is natural log. I don't know why the letters are backwards. My guess is something Latin, but this represents the natural log. So this is kind of like a common log. A common log is always base 10. This one will always have a base of e. So this is essentially the same thing as like log base e of something. Okay? You'll never see me write it that way. It'll always just be ln. So when I say evaluate ln 15, that's just saying put it right in your calculator and do natural log of 15. Okay? And I get 2.708. ln 15 equals 2.708. Let's think about what that means. Remember that this is a common log with a base of e. And remember, the answer to a log is always an exponent. So what does this mean? It means if I take e and raise it to the power of that 2.708, it should come out awfully, awfully close to 15. Okay, might be a little bit off just because of how we rounded that, because the e is going to have to round at some point too. But if I wanted to check that, I can do e to the power of, what was my number? 2.708. And I end up with something awfully, awfully close to 15. Again, off just because of the rounding. Okay, so look at this one. Natural log of e to the power of 7 without a calculator. Well, remember, this is like log base e. We don't really have to write the e. But do you remember we talked about what happens when these two things are the same? That essentially your answer is just this? Really what this question is asking is e to what power is equivalent to e to the 7th power? And then it just becomes a no-brainer, right? That this would have to equal this. Okay, so the correct answer to this question is 7, because essentially you've got the bases matching, and so then your answer is just the exponent. Okay, that's a lot to pack into one lesson. I think it would be great if you took some time to practice with some of these questions, and we will make sure to discuss this next time I see you in class. All right, have a great day.